Hello everyone, I am Shruti Pandey and I will be presenting on the topic cavity ring down spectroscopy. Outline. This presentation will cover the following: introduction, historical background, principle, instrumentation and setup, theoretical basis and data analysis, advantages, disadvantages, application, and in experimental setup and results. Coming to introduction. Cavity ring down spectroscopy is an ultra-sensitive laser absorption technique widely used for detecting very low concentrations of molecules in gases, liquids, and solids. Why it is so unique? Unlike traditional absorption techniques, CRDS measures the decay time of light rather than light intensity. This allows for much higher precision and sensitivity. Coming to importance, it is particularly suited for atmospheric monitoring, detecting trace pollutants, and analyzing reaction kinetics in chemical processes. Now, historical background. CRDS was first introduced in the late 1980s by Anthony O'Keefe and David Deacon, who developed it to overcome the limitation of conventional absorption techniques. The technique has since evolved, being applied in wide range of fields from environmental monitoring to chemical reaction analysis. Early work focused on the detection of atmospheric pollutants such as CO2 and NOx, that is nitrogen oxides. Over time, CRDS has become the go-to method for high precision gas sensing. Now, principle of CRDS. The principle of CRDS relies on measuring the decay rate of laser light pulse in a closed optical cavity containing the sample gas. Coming to how it works. The laser light pulse. First, the laser pulse is introduced in an optical cavity made up of two or more highly reflective mirrors. The cavity is filled with the sample gas that needs to be analyzed. Second, cavity formation and light trapping. The mirror have been very high reflectivity, often above 99.9%. So when the light enters the cavity, it reflects back and forth between the mirrors thousands of times. This repeated reflection effectively traps the light within the cavity, allowing it to travel a long effective path length, increasing the chance of interacting with the sample gas molecules. Light decay ring down. As the light pulse travels within the cavity, a small fraction escapes with each reflection. This escapes causes the light intensity within the cavity to gradually decrease over time, a process called ring down. The rate at which the light intensity decays is monitored by a detector placed outside the cavity, which detects the light that leaks out. Fourth, ring down time measurement. The ring down time is the time it takes for the light intensity to decrease to a fraction of its initial value. In an empty cavity with no absorbing sample, the ring down time depends on the reflectivity of the mirrors. When an absorbing sample is added, the ring down time shortens because some light is absorbed by the sample, accelerating the decay. Fifth, absorption calculation. By measuring the ring down times with and without the sample, the absorption coefficient alpha of the sample can be determined using the following relationship, which is given in the PPT, where K is equals to decay rate, tau is equals to ring down time, C is equals to speed of light, L is equals to length of cavity, R is equals to reflectivity of the mirror, alpha is equals to absorption coefficient of the sample gas. The absorption coefficient is directly related to the concentration of the absorbing species in the cavity. By calculating alpha, the concentration of the target gas can be determined. Sixth, high sensitivity. The extremely high reflectivity of the mirrors allows the light to travel a very long effective path length within the cavity, greatly enhancing the sensitivity of the CRDS. This makes it possible to detect trace gases at very low concentrations, often in parts per billion, that is ppb, or even parts per trillion, ppt levels. Here you can see there is one diagram which is of core components of CRDS. Now discussing core components. First is laser source, a tunable laser which provides light at specific wavelengths suitable for the sample's absorption characteristics. The laser's precision is crucial for accurate absorption measurements. Second, optical cavity. This cavity consists of two highly reflective mirrors, often with reflectivities exceeding 99.9%, that allow the light to bounce back and forth multiple times. This prolonged interaction path is what gives CRDS its sensitivity. Third, photodiameter. A fast sensitive photodetector is positioned outside the cavity to monitor the decay in light intensity over time. The detector's accuracy in capturing the decay profile is essential for calculating decay time. Fourth is data acquisition and processing system. The system which is shown below, it records the intensity decay curve and performs calculation to derive the sample's absorption coefficient based on the measured decay times. Here it is the graph of it. Advantages of CRDS. Talking about advantages, first is exceptional sensitivity. CRDS is capable of detecting concentration as low as ppt, that is parts per trillion, and making it far more sensitive than any other absorption technique. Second is non-destructive. It is ideal for delicate or rare samples. Third is minimal calibration requirements. The ring down time provides an inherent calibration which reduces the need for external reference material. Fourth is broad applicability. It is useful across a wide range including environmental monitoring, combustion diagnostics, and chemical reaction studies. Now coming to disadvantage. First is high cost. It is actually expensive. It requires expensive high reflectivity mirror and stable laser sources, which can increase setup and operational cost. Second is limited wavelength range. The choice of laser source restricts the range of wavelength that can be used for specific application. Third is environmental sensitivity. The performance of CRDS can be affected by change in environmental condition, which is temperature and pressure. Fourth is complex setup. So proper alignment of the optical component requires precision, which can be challenging in field areas. Now coming to application of CRDS, environmental monitoring. CRDS is extensively used for real-time detection of trace gases like methane, carbon dioxide, and nitrogen oxides, which contribute climate change research and pollution monitoring. Now, second is combustion diagnostics. CRDS allow for precise measurement of species such as OH radical and NO in combustion flames. Third is isotopic analysis. It is used in isotope radio studies, enabling researchers to track sources of pollutant and study isotopic signatures in environmental sample. Fourth is biomedicine. Emerging applications include detecting trace biomolecules in exhaled breath for early disease diagnosis. Experimental setup. The experimental setup for CRDS in this study includes the following. First is cavity design. A linear cavity with two super mirrors of reflectivity 99.99% around 570 nanometer was used. Weak acetylene overtone transitions were analyzed. Second, laser system. A coherent CR699 single frequency ring dye laser stabilized with an external etalon was employed. The laser was capable of continuous 30 GHz scans. Third, modulation and detection. An acousto-optic modulator AOM interrupted the laser beam to produce ring down events. Signals were recorded by a silicon photodiode and digitized with a 1 MHz 12-bit PC interface card. Coming to results, these were the graph plotted by the experimental setup. So the results include limit of detection. The CRDS setup achieved a limit of detection as low as 5 into 10 to the power minus 13 per centimeter, demonstrating its exceptional sensitivity. This sensitivity was achieved by averaging the spectra over several days, which helped reduce noise and enhance signal detection. Second is precision. The line center drift during the experiment was less than 4 into 10 to the power minus 8 per centimeter meter, 20 megahertz, indicating the system's high stability over the longest experiment lasting 4.5 days. The relative precision of the measured frequencies provided by the wave meter was better than 3 into 10 to the power minus 4 per centimeter, that is of 10 megahertz. Coming to discussion. First is short to short noise. The signal to noise ratio in the experiment was limited by photodiode noise, making it 10 times higher than the ideal short noise limit, that is fundamental quantum noise level. This noise variation, called short to short noise, affected individual laser pulse measurement but was mitigated through averaging. Second is averaging for sensitivity. Long-term averaging of data significantly reduced noise, allowing the system to detect ultra-low concentration. Third is potential for optimization. Improvement in the photon flux, light intensity, and detection electronics could further reduce noise, enhancing sensitivity and performance. Coming to conclusion. So the conclusion include that it shows exceptional sensitivity. The experimental setup demonstrated CRDS ability to detect trace gases at extremely low concentration, achieving an LOD of 5 into 10 to the power minus 13 per centimeter. This sensitivity makes CRDS suitable for high precision application, that is environmental monitoring and isotopic analysis. High stability. Second is high stability. The system showed excellent frequency stability over long duration with minimal drift in measured line center, enabling reliable long-term measurements. And last but not the least, future improvements. While the setup achieved remarkable sensitivity, the signal to noise ratio could still be enhanced by addressing the photodiode noise and increasing photo flux. Even greater detection capabilities uh, can be realized. This highlights the adaptability of CRDS for further advancement in phase gas sensing. Now, in conclusion, I would say CRDS is a highly sensitive, precise, and versatile technique. Despite challenges such as cost and complexity, it plays a crucial role in environmental monitoring, combustion diagnostics, and emerging biomedical applications. Now, thank you for all your attentions. Presented by BT21 CME 079 Shruti Pandey.